thesis talk this week for application for a PhD position. We can all push something, it will work out. And we will hear about his master thesis, where he derived a kinetic model in the presence of epidemic dynamics. You have the stage.
Thank you. Thank you very much for the introduction. So, as Miki said, in my presentation I'm going to expose my master thesis project that was about kinetic models for well distributions in presence of epidemic dynamics with asymptomatic cases. So, my presentation is divided into 4 parts. In the first one, we're going to explore the epidemic models that we have used and a fitting process that we have performed in order to obtain some significant values for all the epidemic parameters. In the second part, we're going to see the kinetic model theory in general as a reinterpretation of the classical kinetic model for well distribution. And in the third part, we are going to see the couple model, and after some numerical tests and results that we have obtained. So, for an epidemic dynamics, it's common to resort to the classical SIR model, which is a class compartmental model in which the population, the total population N, is divided into 3 classes: susceptible, infected, and recovered. But we have decided to add a new class of asymptomatic cases in order to have a better description for all those diseases that present large cohort of asymptomatic cases, such, for example, the one due to the COVID-19 infection. We have this model preserves the idea of total population conservation, so there is no death and no birth. But we also have the permanent immunity, so there is not the possibility of a reinfection for the same individual. If we want to look a little closer to the model, it is completely determined by 4 parameters: beta, that is also present in the classical SIR model, and is the product between the average contact rate and the rate of the transmission for the disease. C, that is the probability of being asymptomatic infected, and so 1 minus C is the probability of being unasymptomatic infected. And then we have 2 different healing rates, one for each of the classes we have of infected that we have in the model, and consequently also 2 different removal times. The basic reproduction number in this case is a little more complicated, the one for the classical SIR model, and is obtained using all the 4 parameters that we have just described. We have performed a fitting process with the data of the COVID-19 infection for several European countries. But in order to do that, we need to divide the data at our disposal into 2 different parts. In the first phase, we have the pre-lockdown phase, where the data at our disposal are unbiased by all those social distancing policies that may affect the values. And we solve a minimization problem reported here in equation 4 only for the recovered infected and the classical infected, since the asymptomatically infected are not individuated by the healthcare system. We have obtained some significant values for the basic reproduction number that we have reported here, but for all the parameters in our model, more accurate, that are more accurate than the one that we obtain with a classical SIR model. With the second phase, so after the introduction of the lockdown phase, we can obtain a new parameter that is nothing more but a numeric value for the decrease in the social activities due to the lockdown measures and social distancing policies. So now, and all this data will come back at the end of my presentation for the results that we have obtained. The kinetic theory for collective phenomena in general is a reinterpretation of the classical kinetic theory, where we want to identify the molecules of the classical thermodynamical system with agents, the energy of the particles with wealth of the agents, and binary collisions, with wealth exchanges. As it was for the Maxwellian particles, the agents are supposed to be indistinguishable, and their state is completely determined by their current wealth, which change accordingly with the binary interaction, so the wealth exchanges that we decided to use. This type of situation and the evolution in time for the wealth distribution is described by a Boltzmann-type equation. In detail, are specially homogeneous Boltzmann-type equations we have here, and where the collisional operator can be defined by the so-called weak form using suitable test function. Now, this type of equations is very difficult to be solved analytically for every time, so it is common to search only the steady state and the equilibrium for the system that we want to study. In detail, and we will go back there later. In detail, we have decided to use the Cpt model that was first introduced by Stefan Cordier, Lorenzo Pareschi, and Giuseppe Toscani in 2005, and in which the interaction rules are governed by two main ideas. The saving propensity idea, so each agent will only exchanges a small fraction of his wealth in each exchanges, in each interaction, and the concept of a market risk that is modeled by two random variables that are independent and identically distributed with zero mean and fixed variance sigma. What is interesting is that for certain combination of the gamma, that is the saving propensity parameter, and sigma, the steady state that we want to obtain will develop Pareto tails behavior that is quite common for the wealth distribution in the Western countries. So if we want to obtain the steady state, one of the way to obtain that is perform the so-called quasi-invariant limit procedure, where we rescale all the kinetic parameters and the time with a new coefficient, epsilon. And the idea is that in the same interval of time, we are performing more and more interactions, but each interaction only changes very slightly the wealth of the agents involved. From this type of procedure, we are able to obtain from the Boltzmann-type equation a Fokker-Planck-type equations, for which is easier to obtain, we can obtain explicitly the steady state, which results to be an inverse gamma distribution as reported here, and for which we have the Pareto index as we have said before. So now we can go to the couple model, where we have divided the global wealth distribution into 4 different distributions, one for each of the cluster that is present in the epidemic dynamics. The number of agents belonging to each class is obtained integrating the specific wealth distribution over the wealth. We still have the global mass preservation, so the total population preservation. And from the CPT interactions, we have borrowed the idea of saving propensity and market risk modeled by random variables. And now we have obtained a Boltzmann-type system that is composed by 4 different Boltzmann-type equations, but this time these equations are not anymore spatially homogeneous, since we have also a reaction term that is due to the epidemic dynamics. In details, the reaction term depends of function, beta, that is the coefficient that we have seen before in the CR system, is now a function of the wealth, in the sense that it is reasonable to assume that a person with high wealth is likely to encounter and exchange money with another person with high wealth than with one with lower wealth. But from now on, we will only use beta for sake of simplicity as a constant. So we want to obtain the steady state, but before we can do that, we need to prove that there is convergence and also existence for the steady state, for the equilibrium. And in order to obtain the convergence, we have resorted to a family of Fourier-based metrics. In detail, we were able to prove that given two different solutions corresponding to two different initial values and imposing a bounding condition for the kinetic parameters, it holds that the d2 distance of these two solutions decays exponentially in times as reported in equation 15. Now, for the existence part and uniqueness part, we need to introduce a new a set of probability measures with fixed first and second moment, and the D-infinite space that is a product space of 4 of this type of sets, and the D overline D2 metric that is nothing more but the metric that we had here before in the previous theorem. And then we were able to prove that if the initial value belongs to the infinite space, then the Boltzmann-type system has a unique steady state, and it also belongs to the infinite space. Now we want to obtain explicitly the steady state, and in order to do that, we perform again a quasi-invariant limit procedure. We scaled all the parameters, both kinetic parameters and epidemiological parameters, and now we have to think that since we have not allowed the reinfection for large time limits, so for the equilibrium that we are looking for, there is no possibility that there are still infected symptomatic or asymptomatic. Since once the total population has reached the herd immunity, the number of infected is going to decrease to 0. So for large time limit, we will only have 2 Boltzmann-type equations, and so only 2 Fokker-Planck equations, one for the susceptible remain and one for the recovered that we have obtained. And for both of them, we were able to obtain explicitly the solutions, and both of them results to be gamma inverse distribution, and the global steady state is nothing but the sum of these two distributions. Now, as we can see here, the behavior of the global steady state is not unique. It could present a unimodal shape that is quite common for the Western countries, but it could also present a bimodal shape that is considered to be a sign of high stress in the economy, since, as we can see here, we have a new poor class in the wealth distribution. So it is reasonable to assume that is the effect of a pandemic. Now we can proceed with the numerical test that we have performed. Firstly, we have studied a simple Cpt model with some Monte Carlo simulation, direct scheme simulation. And so we have sampled a larger number of agents, and we have performed a huge number of interactions. And in order to see if, as forecast by the quasi-invariant limit procedure, we obtain the equilibrium that we have obtained solving the Fokker-Planck equations. And as we can see here, as epsilon decays to 0 in the simulations, we obtain a convergence for the well distribution to the Fokker-Planck solution that we have obtained theoretically. Then we have performed some numerical simulation for the coupled model. And first of all, we need to think that since the asymptomatic individuals commonly do not know that they are infected, it is reasonable to assume that they do not change their habits, and so they have a higher contact rate, so a different beta from the symptomatic one. So we have focused our attention to the Italian case for COVID-19 infection, and we have performed some simulation and obtained values for different Mi parameter, that is the rescaling factor for the interaction activity. And what we have observed is that in absence of lockdown measures and using specific values for the kinetic parameters, we obtain an unimodal shape that, as we can say, is the most common well distribution for Western countries with Pareto tails. But what is interesting is that if we use, of course, here we have performed the simulation avoiding the lockdown measures. So we have obtained the data of the first part from the first part of the outbreak of the COVID-19 infection, and then we have only simulate the situation without any social distancing policies introduction. So as we can see here, in this unrealistic case, the COVID-19 infection would have disappeared by the end of July of the last year in Italy, since by mid-April we have reached the peak, and so then the infected are going to zero, are decaying to zero. In the more realistic case, where we are considering the lockdown measures, what we obtain with specific values for the kinetic parameters is indeed a bimodal shape for the well distribution, so the formation of a first peak of poor in the well distribution. And so in conclusion, we have coupled these two models, we have obtained some numerical, we have obtained values for the epidemic parameters that are more realistic and more reliable than the one that we obtained with a simple SEER model, using also the asymptomatic cases. We have combined these two, the kinetic model for the kinetic model for wealth distribution with the SEER system, and we have proved convergence, existence, and uniqueness for the steady state of the Boltzmann-type system that we have obtained. And we have also seen that depending on the behavior of the pandemic and on the kinetic parameter that we use, the steady state of the well distribution would present unimodal shape, but also bimodal shape. And that's all. Thank you very much for the time.
Are there any questions? Yes.
First of all, thank you for the interesting talk. You can return to the first slide with the field equation for the model, the differential equation for the SEER and SIRE model.
Yes, of course.
Okay. Behind this equation, there is a strong assumption, which is such a mean field assumption, which means that everyone can interact with anyone.
Yeah.
Okay. And so, in some sense, this is somewhat unrealistic.
Yeah.
Okay. Coming to the question. Have you tried to consider the model in network with different topologies, such as Barabasi-Albert network, so scale-free network, and small world communities, and if you foresee any technical difficulties of all the rest of the analysis in this case?
When we have studied only the epidemic dynamics, since it was not the core of the thesis, we have restricted ourselves only to consider this simple case. But when we were talking about the coupled model, we have introduced a dependence, at least at a theoretical level, of the interaction on the wealth. So also the healing rates and all the epidemic parameters depends in the more general model on the wealth of the agents. And so the wealth of the agents is I don't know how to say that, but as I said before during the presentation, it is reasonable to assume that individuals with almost the same level of wealth are interacting together more frequently than those with high different wealth. And but no, we haven't used any more complex. We have only relied on these two ideas of the kinetic system and the classical SEER model, but it could be also a new way of introduction, a threshold and also a rule in the interactions amongst all the individuals involved. It could be quite challenging from a numerical point of view, but theoretically, yeah.
Yeah, because I think it's interesting because with the introduction of asymptomatic cases, of course, if a big spreader in a scale-free network is symptomatic, is okay because you can cut any link with the other nodes. But if this is asymptomatic, that would be a mess in the sense that the infection would spread across all over the network.
Yeah.
And also for the point of view of the COVID-19, because of at least in the first stage, the role of asymptomatic big spreaders was very heavy.
Yeah, it's true. It's true. The data that, if we study the data at our disposal for the COVID-19 infection without the assumption of a large cohort of asymptomatic cases, we obtain some unrealistic values. Also for the basic reproduction number, we obtain values higher than 7 or 10, and those values are not reasonable to assume that they are valid. So no, yeah.
If I understand well, those beta is a sort of interaction kernel.
Yeah, a sort of, yeah.
If you take those beta non-constant, is it possible to obtain analytically a steady state, or you have
it is
problem with the interval because you cannot...
the weaker hypothesis is to have L1 beta, but we haven't proved any result in this sense. The idea, also the result that I have exposed here, is not really strong. As we can see, the initial values belongs to this particular space that I haven't described accurately, but these values are the asymptotic values for the susceptible, the infected, the asymptomatic, and the asymptomatic infected, and the recovered of the first and second moment for the distributions. And so, as I said before, for large time limit, these values disappear. This is 0, 0, 0, 0. So, in reality, we have proved the existence for a problem very easy, where we have only these two equations without this term, only the kinetic interaction.
In Q,
Yeah.
the interaction, there is no interaction kernel.
No. In Q, we have used. For sake of simplicity, we have always used Q only through its weak form. The kernel, we have the kernel that it depends at a theoretical level on sigma, on the sigma of the kinetic parameters, and on the integral of the infected, if I recall well, and but we always prefer to use the weak formulation where the kernel is not present, and so.
Yeah, I think it's not possible.
Yeah.
Steady state solution.
Yeah. Analytically, no. I think that's true.
No problem in principle. But theoretically.
Any other questions? I have one. If you would allow reinfection, our steady state would have like a constant amount of infected people at one point.
It depends on the behavior of the infection. For example, I don't know the noun in English for morbillo, the word for smallpox. It's a periodic infection. So it reached the herd immunity, disappear, and then reappear again. And so if it is the case for the model that we studied, that it's not necessarily related to the COVID-19 infection, the well distribution may present the steady state could present a problem. It could be a problem to obtain a steady state since this behavior. But if the infection is allowed but sorry, but with very different epidemiological parameters. For example, very parameters that are smaller than the ones that we have before, since the also the capability of infection of a person that has taken twice the same infection is lower than the one that is taking for the first time. Maybe we would have reached an equilibrium. The thing is that if this epidemic model reach an equilibrium, we could obtain also easily an equilibrium for the coupled model. If the CR system is describing an infection with not an equilibrium but a periodic behavior for large time, I don't know if we would be able to obtain an equilibrium.
Thank you very much. Any other questions? Then let's thank again the speaker.